So we are going to be looking at today section 11.4. We just finished on Monday the integral test, which is a long test. I mean, each of those questions, if you do them properly, is going to take you a long time. So we're now moving on to a different type of test. So there are actually two of them. One of them is called the limit comparison test, which is the major one, the one you'll use most of the time. And then we have a backup test called the comparison test. And first thing we're going to do is look at how do you create this second series called the comparison series. So in the comparison test, essentially the logic of it is like this. I've got a series called sigma AN, and I don't know if it converges or not because the way it's written, it doesn't lend itself to any of the previous tests we talk about, right? The integral test doesn't work, or I don't know how you make it work because it's weird, whatever the reason might be. We can't use the test that we know. So what we do is we take this guy, this sigma AN, the original, and we find another series, much simpler looking, but behaves the same way as it, and it's called the comparison series. And then you look at what does the comparison series, the easy one, do, and you look at it compared to your original, and from that you can make a sensible conclusion. So first thing I'm going to do is show you how you create this new guy, the comparison one, right? It should be simple. Now, first type we're going to look at, I guess we'll call it A, are rational functions, or rational expressions, I guess would be a better term. So if you get a series and it's made up of a fraction, and the top and bottom are powers of n, they could be n cubes, n squareds, that would be a good candidate. So I'm going to say 2n squared plus 1, right? And on the bottom, I'm going to do 4n cubed take away n, right? I know, plus 7. Let's make it ugly. Right. Would you agree that you couldn't do an integral test in that even if you wanted to, because integrating fractions like that at least are not really doable. So this is the original function. This is the guy that we call AN, right? Sigma AN. And this is how you find its comparison. I call this method surgery. Just a made up name, it's my name. And you put in funny little wobbly equals lines, just like the OC symbol. And that symbol means, depends how you want to phrase it, approximately equal to, or you could say behaves the same as, or you could use the phrase equivalent to, right? So I'm going to take this guy and I'm going to simplify him. And the new guy, this one here, that's going to be my comparison series. The way you do it is quite simple. Take the biggest power on the top. Do you see it's 2n squared? Put that down. On the bottom, take the biggest power, which is 4n cubed. And then you can simplify that. And it's that. Now, a slightly different version of the same situation. And me personally, I think this is a little bit easier to deal with. I don't even care that it's 2n squared. I just care that they're on n squared. And I don't care that it's 4n cubed. I call it that. So, I mean, the answers to the comparisons are quite similar. Would you agree? They're not an awful lot of difference. It's just that if you do this version, you tend to get pretty much the simplest series in the world. So this guy here, that guy there, is the comparison series. That's the guy we call sigma Bn. Now, we know what that guy does, don't we? Do you recognize that guy's a harmonic series and it diverges? So I can tell you right now, although I haven't proved it, that this series diverges. Why? Because it behaves like its comparison. Now, there's a lot of work to do to prove that, but that's essentially how we're going to do it. Same situation, but a little bit trickier this time. Let's suppose I was wanting to do that, right? That's my sigma an. Then I take the square root of n squared plus 1, right, on the top, and the square root of n cubed plus n on the top, the bottom. And let's do the surgery on it. What would the square root of n squared look like if you basically got rid of everything except the highest power of n? Well, it would look like that guy who's n. Great. Now, what about the square root of n cubed plus n? It would behave like n cubed. And the square root of n cubed is n to the 3/2. This expression can be simplified. We agree there's n and n thingy. That ends up being 1 over n to the half. And that is my comparison series, that guy there. Do you see how this works? You take your original and you basically cut off all the bits that don't matter, right, surgery, and just leave behind the biggest power of n on the top and leave behind the biggest power of n on the bottom, and tidy it up as much as you can. And once you can't do any more, basically 1 over n to the half in this case, that's your comparison series. Now, there are two major types of comparisons that we use. The first one we've talked about is rational. The second one is geometric. So that would be a series that looks something like this. 2 to the n, oh, let's make it n plus 1, and 4 to the n over 7 to the n plus 1, right? See that guy there? Let's do his comparison then. I have a choice between 2 to the power of n plus 1 and 4 to the power of n. You pick the biggest power. Now, the biggest power in this case is 4 to the n, not the 2 to the n plus 1, because isn't 4 to the n going to be a lot bigger than 2 to the n plus 1? Think of what it would look like when n's a billion, right, of the American debt, right? 4 to the American debt is going to be 2 to the American debt plus 1, right? It's essentially going to be twice as big if you want to know. So you pick it. Now, on the bottom, I don't have anything, but let's put in a plus 3. Let's pretend there's a plus 3 there, right? Now, that one's a little bit easier. Would you agree that's 7 to the n plus 1? Now, what that is going to become is a geometric series, right? And right now, it's not quite there because I've got n here and an n plus 1. So I'm going to do this. Oops, I should be able to put my little squiggly lines in. I'm going to make them both the same. And you might say, but wait a minute, you've dropped one of your powers of 7. Yeah, I've dropped to 7. But in the big scheme of things, isn't 7 trillion and a trillion still basically big, right? It's not going to make any real difference. That is 4/7 to the power of n. So your comparison series, in this case, is the geometric series 4/7 to the power of n. Now, if you remember the geometric series, isn't the only thing that you need to know is the common ratio to decide is it going to converge or not? When you look at that guy, can you tell that the R value is 4/7 and so it's going to converge? Now, that is not a proof. That's me just knowing the answer before I prove it. And we have to prove these things. But I know it's going to converge. In the same way that I know this one's going to diverge. And so is this one. Let's try another one. Forgot to write it down here, didn't I? Right, let's see if we can make life easy by doing as much of the surgery at once. Would you agree the top is 3 to the n plus 2? Because it's the only thing that's there. but I'm going to call it 3 to the n, because remember, I want a simple answer, right? 3 to the n. It's basically 9 times 3 to the n, so I might as well just call it 3 to the n. Which one of those two in the bottom, the 5 or the 3, is going to be the winner? Which one's going to be important?
5.
Right. And I know it says n plus 6, but can't I just call it 5 to the n? Which means that this thing is going to be that guy. And so my comparison series is going to be this geometric. In other words, this guy is going to behave like that guy. And do you notice that that guy is 3/5? That means this one here also converges. Now, if that was 7/9, it would converge. But if it was 9/7, wouldn't it diverge, right? So finding the comparison series is only one step in the process. But a lot of people get switched off by that. And I can tell you in the homework you'll want to be, because you already know what the answer is going to be. So you want to hit that little dot saying diverge. And in your homework, nobody will know that you hit the right button. You know, you hit the button for the right reasons. But in a test, if you stop here and just say, oh yeah, it converges, or oh yes, it diverges, that's not proof, right? It's not finished in the process. But that's step one done. How do you find the comparison series? So are you okay with that? So if I gave you a rational function, you know, 1 2 powers, or I gave you less common, but I gave you a geometric one, would you feel comfortable you could find the guy to compare it against? It's all about surgery, right? Only taking the important part from the top and from the bottom. Now, the second thing, which series converge and diverge? Well, we've already done that, but I want to show you it kind of summarized. You know, you're going to get the answer 1 over n cubed, 1 over n to the half, 1 over n squared, you know, that kind of thing. When did they converge? Well, this series here is called a p series, right? So if you get 1 over n to the power of a number or a fraction, it's called a p series. If this power, this p, is bigger than 1, the series converges. So 1 over n squared converges, 1 over n cubed converges, 1 over n to the power of 1.1 converges. On the other hand, if p is less than or equal to 1, this series will diverge. So 1 over n diverges, 1 over n to the half, 1 over n to the 3/4, those diverge. Now, if you get a geometric series, won't they look something like this, right? 3/4 n, 5n, whatever. I'm calling it r at the end. If this common ratio r is greater than or equal to 1, this series diverges. And if this common ratio is less than 1, this series converges, right? These are the only two guys you really need to remember, memorize, whatever the word you want to use, for your comparison test. When you end up with a p series, you want to know what this is, right? You want a geometric, you want to know what this is. I already actually said that in the earlier stages. And that's step 2 done. Well, maybe I should pause a minute. Okay. Does this p series converge? Yes or no? Say a nod, that'll do. Does this series converge? No. Equal to 1. What about 1 over the cube root of n squared, which is not the way I would write it, but isn't that 1 over n to the 2/3? Does 1 over n to the 2/3 converge, or does it diverge? 1 over n to the power of 2/3.
It diverges.
It diverges, right? So isn't it quite easy to tell if you have a series that looks like these p series, which ones work, converges, and which ones fail, diverges? I'm going to do 2 of these guys. There's 2 geometric series, right? Very, very basic ones, right? They don't even have an A at the front, but isn't the R value 3, 7? and this one it's 4/3. Which one of these two converges?
3/7.
Right, and won't the 4/3 be the diverging one, right? So if you have a comparison series, it will look like one of these 5 guys, won't it? It'll look like these guys. And won't you know whether it's going to converge or diverge as your final answer, right? You'll know what the final answer should be even before you've got to it. So far, so good? Right, now, moving on to step 3, and that is the limit comparison test itself. This is the whole process. And it says the following. For any series, sigma an, if the limit of an divided by bn equals a number, right? So it's not allowed to be 0. 0 doesn't count as a number. It's not allowed to be infinity. That also doesn't count as a number. So maybe I could say not 0 then, right? If it's a number like 42.5, doesn't matter, right? -8, doesn't matter. As long as it's a number, then the top guy will behave, sigma an, will behave exactly the same way as its comparison series behaves, right? So we've already mentioned that, right? This guy behaves like that, it's going to converge. This guy behaves like this fella is going to diverge. And formally then, if this converges, then so does your original converge. If this diverges, so does the original diverge. And when we do this, we're going to do it in 2 main types of questions. They're going to be series that look like fractions, you know, like this one, or, and that's most common, or fractions that look like this, right? Now, the top ones, don't they tend to generate P series, and the bottom ones tend to generate geometric series. So that's what the limit comparison test says. Now, the last part says, when do you use a comparison test? You should only use it, or you should always use it, in every situation that looks like these two. So if you ever see a fraction with powers of n, n cubed, square root of n's, top and bottom, use this test. If you see nothing but 2 to the n's and 3 to the n's and 5 over n, things that look like that, use the limit comparison test. There is a second comparison test. It's just called the comparison test. So you have limit comparison test is the major one, but there's a backup plan. When your series has unusual terms in it, then you need to use what is called the comparison test. An example. If I had wanted to know, does that converge or not? Do you see it's got a sign in it? So if it's got a trig, right, a sine squared, a cosine cubed, a tangent, an inverse tangent, right? Weird stuff. That's what I mean by unusual, right? It doesn't have n's and n squares, right? It has that guy. E's, right? E to the sine n, e to the 1 over n, right? Weird stuff like that. You're getting a feel for what I'm talking about here, right? So this is much rarer, right? If you're looking at limit comparison test, 80% of the questions you do are typically limit comparison test. Only 20% of them are that. Students, on the other hand, want to use this test 80% of the time, and that other one, the limit comparison, 20%. And I know why they want to do it, because when you see it, you're going to say, oh, that's dead easy. Can't I use it for all of them? No, you can't. If you use it for all of them, half the time you will be right, and half the time you will be wrong. Do you want to do an exam where you're guaranteed to get 50%? That's not going to work, right? You're going to love the comparison test. You're going to say, God, it takes 30 seconds. That other one took 10 minutes. 10 minutes, 30 seconds, I can understand. But you've got to resist the temptation. So let's return now to comparison test questions, and I'll jump in with a very simple one to start the ball rolling. And it looks like that. First thing I'm going to tell you right now is I've already started doing it. But from now on, if I write that down, will you just assume that it's got the other bits? It just saves 10 seconds every time, but that adds up. Nothing wrong with you doing that as well. So back to this one. I am going to do some surgery on this guy to find out the comparison test. Would you agree that the surgery is pretty easy to do? The top's still 1 and isn't the biggest power n to the 5. So far, so good? Are you comfortable with the comparison? That's a p-series, isn't it? It's a p-series. P is equal to 5. And since that's greater than 1, I know that it's going to converge. So now I have to prove it. Right? If the P is bigger than 1, it converges. If it's less than or equal to 1, it diverges. So we now move on to the limit as n tends to infinity of an over bn. This guy here is an, and this guy here, the comparison guy, is bn. So you're going to be looking at the limit as n tends to infinity of an divided by bn. And it's not uncommon to get fraction divided by fraction, right? That's messy, but that's what you're going to get. Can anyone tell me a short way of dividing by a fraction?
Multiplying by its reciprocal.
Okay, so essentially what I'm going to be doing is that guy times that, right? Multiplying by its reciprocal. Now that I've done that, I can put it together and get that. And a lot of people go from this line to that line pretty quickly. Right, I just need to find what that's equal to, and as long as it's a number that's not 0, I've essentially finished the question. And there are pretty much always going to be 2 ways to do this limit. If you think back to Calc 1, couldn't I do L'Hopital and get the answer that way? And hopefully you've seen the other one. Have you seen the one where you divide the top and bottom by n to the 5? You've seen that method? Ring any bells? Right, here it goes. I could do L'Hopital that, and by all means do that, but here's a trick that you can use. As long as you do it to the top and bottom, it's okay. So this thing now becomes the limit as n tends to infinity of 1 over 1 plus 8 over n to the 5. You can then just brute force it by making n infinite. A over infinity is 0. 1 over 1 is 1. Haven't we found the limit as 1? Now, if I was going to do L'Hopital, wouldn't I differentiate the top, differentiate the bottom, and I'd get the same answer eventually. So far, so good. Now, according to the limit comparison test, if my guy converges, then this guy converges. Now, was the limit a number that's not 0? Yes. So you just need to go and do this. By the limit comparison test, the series converges. People want to stop there, but this is the proof that you're allowed to get to the end that is acceptable mathematically. Are you comfortable with that question now? Limit comparison test. That was one of the simplest ones you can do. So let me just pick something uglier. Question 6, kind of going to the extreme here. This one is the cube root of k over the square root of k cubed plus 6k plus 4. And I want to prove that that converges or that diverges. We'll find out in a minute which it is. Let's do the find the comparison. Nothing to do with cube root of k. If you've only got one guy, that's who the answer for the top piece is. Now the cube root is better written as a fractional power, so I'm doing that. Would you agree the bottom is the square root of k cubed? You agree? Highest power is k cubed. Square root of k cubed. But that should be written as 3/2. And now I need to figure out what that looks like. Well, I'm basically just going to let the calculator do it for us. If you take the top power, which is 1/3, and you divide it by the bottom power, which is 3/2. Okay, 1/3. I'm saying divide. Top guy, 1/3. Take away the bottom power. That's how you do it with powers. And then go math, make me a fraction, and you get that guy. And since that's a negative power, it's the same as 1 over positive 7/6, right? K to the negative 7/6 is the same as 1 over k to the positive 7/6, right? That's the P series. The P value is 7/6. Does that converge?
Yes.
So you put in greater than 1 to tell people why you know it converges, and then you can just say converges. Now you might say, why do we need the limit part? Why can't I do this? Sometimes people will screw up this, and the comparison that they create is not a true comparison, right? It doesn't work. The limit part fixes that. One of its jobs is to convince that you've chosen a valid comparison. So here goes. I now have to find the limit as n tends to infinity of an, which is the original, divided by bn. So that's an. And that's the comparison. So this ugly mess, right, and it truly is an ugly mess, is going to be the cube root of k all over the cube root, or sorry, the square root of this guy plus this guy plus 4. That's the top. It's going to be divided by 1 over k to the 7/6. And that becomes that fella. And then turn this fella upside down. That's a third and that's 7/6. So let me add a third and 7/6 together, see what we get. And that's 3/2. So that's the top guy. And that's the bottom guy. And I've forgotten to put in, so I'm going to put it in here. All the way through, there should have been a limit as n tends to infinity going on, right? Should be 1 there, and so on. This isn't quite in the format that's going to allow me to figure out this limit, because I've got a fractional power up the top, and I kind of needed it because of what was going on up here. But now that I've got a nice answer, I've still got a square root in the bottom. I've got a cube, kind of fractional power on the top. So I'm now going to do this. Okay. I'm now going to combine them. Like that. So far, so good. Now, I can find the limit of this ugly thing by switching places. And you're allowed to do that, right? The limit of a square root is the same thing as the square root of a limit, right? They can switch places, which makes life easy. Can anybody tell me what this ugly fraction is going to have as its limit?
1.
1. Couldn't I do it by L'Hopital's rule or divide top and bottom by k cubed? Can we just pretend I did that because it's a time issue? What we now have is 1, and the square root we're on is 1. And isn't that good news? Because according to the limit comparison test, if the limit is a number that's not 0, we're done, right? So we can now say by the limit comparison test, the series, which is that guy there, converges. So we went from one extreme to the other, right? We went and did the first one we did was kind of babyish, right? There wasn't really any heavy duty algebra. This is like at the other end. Would you agree this is really messy fractions and you have to be careful, right? So most questions are going to be between those two extremes. Let's find another one. Okay, it's question 9. Right, that's the guy. Okay, let's do some surgery. What would the top become? What's this going to be?
N.
What's the bottom going to be?
N to the 5th.
And that simplifies down to 1 over n to the 4. And not a surprise, because you're going to get P series when you have these guys, right? They're all P series when they look like this. So this is a P series. P is equal to 4, which is greater than 1. I keep picking convergers, don't I? So this is going to converge. Now, limit comparison test. The limit as n tends to infinity of an over bn. That's an up there. So it's going to be n plus 1 over n to the 5 plus n, it's the top guy, divided by 1 over n to the 4. That's going to be the limit as n tends to infinity of n plus 1 n to the 5 plus n times n to the 4 over 1. And that, after a little bit more work, becomes n to the 5 plus n to the 4, and on the bottom, n to the 5 plus n. Have you noticed that 1 is a very common answer for the limit? And that is because of the way I created the thing, right? Very often, if you create them to look like this guy, your answer will be a nice number. Not always 1, but a nice number. Okay. Can I put in the number 1 there without proving it? But you would have to. Can I do L'Hopital or divide top and bottom by n to the 5 and I could prove that it was 1? And it is. So we can finish with, so by the limit comparison test, our original series converges. And it converges, right, because of that. Its comparison converges, so it converges. For the next question, I'm not going to do the whole thing. Let's just find the comparison part, right? So in question 10, let's find Bn. So this is what the guy inside the sigma looks like. And we want to find a comparison for it, right? So approximately equal to. Isn't n plus 3 essentially behaves like n? If you're wondering how this works, think of n as being extortionately, extremely big. Would you agree a billion, 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 and a billion, 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 billion plus 3 are so close to each other that they don't make any difference, right? American debt, and then we spend $2 more. Do you think it's going to make any difference to American debt, right? It's huge, right? Now, n plus 2 to the 5. Anybody want to tell me what single power of n this is the same as?
N to the 5th?
Yes. Isn't that nice that you don't have to FOIL that out just to find out the answer is n to the 5? Because if you did, you would eventually come to that conclusion, which means, guess what? I picked another converger, haven't I? I'm sure there's a diverger out there somewhere. I just can't pick it. Right? Wouldn't that be a P series? P equals 4. 4 is bigger than 1, so it converges. And then you do, the stuff that comes after that, which I'm not doing. Okay. Anybody else want to do? Right. I want to do some geometric now. So still on the limit comparison test. First one is going to be this one. Too late, I put that in. Normally I won't. Okay. This is because of what it's made up from. Isn't this going to be a comparison to a geometric series? Can you tell the shape of it? Right. The top guy is 4 to the n, and I think it's pretty obvious that the bottom guy is 7 to the n. So far, so good. That is the same thing as that guy, right? Now, for a geometric series, this fraction is called the common ratio. In this case, it's 4/7. And the rule is that if it's less than 1, it converges. So I know this is going to converge. Let's prove it now. It's going to be the limit as n tends to infinity of an, which is that guy, over bn, which is that guy. So it's going to be 4 to the n over 1 plus 7 to the n divided by that guy. Now, I could use this one, but actually this is a much better version to use, right? Not the combined version, but the separated version. So I'm going to call it 4 to the n over 7 to the n. And that means I can now turn them upside down. So it's going to be that guy times 7 to the n over 4 to the n. So far, so good. Now, sometimes you get lucky. Would you agree they cancel? Doesn't happen a lot, but if it does, use it. So I'm now looking at the limit as n tends to infinity of 7 to the power of n over 1 plus 7 to the power of n. I know that the answer is going to be 1. Can you just tell by looking at it it's going to be 1? But we kind of have to prove it. I could do a very similar technique to the power ones. Couldn't I just divide the top and bottom by 7 to the n? Now, if I'd went that road, this would become the limit as n tends to infinity of 1 over 7 to the n plus 1. And then couldn't I do a brute force? 1 over 7 to the infinity, which is 0. Boom, 1. And then you can finish with the limit comparison test, series converges. What other method could I have used if I wanted to do this and I just don't like this technique of dividing? How else could I have found that limit there?
The Hospitals.
Yeah. And if you differentiate 7 to the n, you get 7 to the n times the natural log of 7. And on the bottom, you'll get 7 to the n times the natural log of 7. Everything cancels and the answer's 1. So it works quite nice.
Professor, can I
Yes.
ask- Okay, thanks. So the problem before this, where we had like the n+3, or the over n+2 to the 5th, and anyway, the P series ended up being 4 greater than 1.
Mhm.
Oh yeah, that one. So do we still do the limit stuff, like the proof on that one?
Oh,
Even though
yes,
it's
you
not
do. I've just skipped that for time purposes.
Okay, because I thought,
And-
yeah, you showed
that,
us these
that
earlier.
one,
So,
yeah, that one's going to be ugly to do because you're probably going to have to do the L'Hopital to prove it.
oh, got it. Okay, thank you.
Right, but it's not pretty. It's doable, but it's not pretty. Next fella, who have we got? How about this one? This is question 8. Right, the top guy, 5 to the n, agreed. What's the bottom, the denominator, going to look like when you simplify it, when you do surgery?
4 to the n.
And isn't that guy, right? And the R value is 5/4, which is bigger than 1. Converges or diverges based on what I've just written.
Diverges.
And so guess what? We finally found one that diverges, right? Just to show you can get them. So now let's prove it. The limit as n tends to infinity of that guy divided by this fella. So you've got that guy times this guy. You see, we got lucky with a little bit of cancelling. What's the limit of that fraction going to be as n goes infinite? Just looking at it, you should be able to tell me. And it shouldn't be a surprise because a lot of answers end up being this number.
One.
Prove it by L'Hopital's rule. Prove it by dividing top and bottom by 5 to the n, whichever one you like, but prove it nonetheless, and it ends up being 1. So by the limit comparison test, the series actually diverges. Let me show you a question where it might hopefully convince you why you need to do the limit part. Let's say we have this guy. And you might argue that that guy, right, this guy here, you might argue that this guy here behaves like 1 over n. And hopefully you say, nah, but you can imagine someone did think that, right? Now, according to what we have here, right, we have a 1 over n, p series, p is equal to 1, that makes it diverge and all that, but let's see what happens when we try and do our guy. Well, an is this scalar, and bn is that. The n's cancel, and I end up with, and if you do brute force in this, the log of infinity eventually is infinite, and so that answer is 0. Do you see that the limit is 0? And remember what the limit comparison test says, it has to be a number that's not 0. What that is telling me, indirectly at least, is that guy there is not a good comparison, right? It's not a good comparison, right? And so you would need to find another version of how you might tackle that question. Are we good so far? Limit comparison test, some with geometric, the others with p-series. Now I'm going to show you one that I deliberately kept away from our list because it is a real stinker. Or if you prefer, it's a really interesting challenge. Right. Get it set up. And let's show you what it looks like. The first two questions are really all about the limit comparison test. There's some of the guys we've already done. There's the guy. Oh, come on. Is that not one ugly, ugly series? Okay, what does the top behave like? There's the first question. What does 4k minus 1 times k squared minus 1 behave like? Do the surgery.
Question, is there any way I can reduce it down? Because I see some pattern here.
What pattern do you see?
For the k squared minus 1 and k plus 1.
Oh, that'll happen later. Yeah, that cancelling will happen later. But right now, we'll just take it as it is and then we'll cancel it down, because the reason it'll happen later is you'll get a k to the 4 on the top and a k to the 6 on the bottom, and they'll cancel that way, right? So I'm going to cancel it after I've done the surgery, not kind of before. Okay, so back to my original question. What is the power of k that the top behaves like?
Cubic?
Didn't catch that. Can you say it again?
Cubic?
Yes. 1 from here, 2 from here. The top is k cubed. What power of k is the bottom going to be? So the top would be k cubed. What would the bottom be?
It's a k5, right?
Correct. Now, k cubed on the top and k to the 5 on the bottom, doesn't that get you 1 over k squared? So I'm doing the cancelling that you were thinking about yet at that point, right? 1 over k squared. That's a p series and it converges. Good luck doing the algebra, but it does converge. Actually, wouldn't the only way to do that would be to blink and foil everything out and then, you know, cancel this and la hospital at the end. Really ugly question. Glad you're doing it, not me. And we are finished with limit comparisons. That's all I want to do with those. So the other half of today is going to be what is called the comparison test. Right? I wish their names were a lot different sounding so it would be easier for you to get used to. But limit comparison test has the word limit in it. which means you're going to do the limit of AN over BN, right? Maybe that's the way to remember. Limit comparison test uses limits. Comparison test does not. So here is our first comparison test. Well, let me check. There might be one before that one that I'm about to do. That's good. Nobody there, none of you comparisons. Good, good, good. There we are. It was, in fact, the one I picked. These are, in one respect, a lot easier to do. Right? I need to find somebody that this guy is bigger than, that diverges. And I'm going to tell you that he's greater than or equal to that guy. And I'm stating that as an obvious fact. Now you might say, well, what's obvious about it? When you do a fraction, right? If you're comparing the value of one fraction to the value of another, right? The one that has the smaller number in the bottom, won't it be the biggest fraction? Right? A half is bigger than a tenth, right? Would you agree that log n is a smaller number than n is? Right? A log of a million is only 6, right? And a million's bigger than 6, right? So the comparison test is all about finding this guy and doing it in a way that you could justify correctly. So I'm going to say that is true, and you're going to agree with me, yes. Right. Okay. Now, then that means that this, that means that this fella is greater than or equal to that fella. Would you agree? If you add all these up for n, you'll add up these. This is bigger than that. What do you know about this fella? Do you recognize 1 over n? What do you know about him?
It's a harmonic series.
Right, a special case of the P series, the harmonic series. Isn't P equals 1, so it diverges? You agree? P equals 1, diverges, harmonic series. So P equals 1. That guy is, less than or equal to 1, so it diverges. Now, if that guy diverges, that means he adds up to infinity. If you've got somebody who's bigger than something that adds up to infinity, would the logic be that this has to be more than infinity? Or at least as big as? So conclusion, by the comparison test, the series converges. So if I can prove that you're bigger than a divergent series, aren't I proving that you diverge? That makes sense? Now, what would happen if I could prove that you were smaller than a series that converges? So I have a series and it's smaller than another series, but that other series converges to whatever it is, 42. What can you say about the original first series, which is smaller than it?
It as well converges.
It converges as well. So basically, aren't you just doing comparisons? But they're kind of ugly functions to do them with, right? They're not particularly nice. So here is another comparison test. And the trick is to find somebody to compare it to. Okay, so I'm going to start with this fella. Now, I know this guy converges. That's important. Now, since I know he converges, and you might say, well, how do I know it converges? Isn't e to the n massive and 1 plus sine n isn't? So it's going to get to 0 pretty quickly. So I kind of know it's convergent. So I need to take this guy and I need to make him less than or equal to somebody else. Would you agree that that is true? or at least most of the time true. We'll be generous. Now, if I wanted to be sure, what could I do? Actually, I should put a square in that to be absolutely certain. What can I do? See if they've got a clue for me. Because that's strictly speaking not always true. And I need to find something that is always true. Or at least true for most of its life. We can get away with most of its life.
2 over e to the n, maybe?
Why not 10? I'll be generous. Yeah. Would you agree that is true? Right. Okay. Now, do you recognize that guy as basically 10 times 1 over e to the n? Which is 10 times 1 over e to the n. Do you see it's basically just a disguised geometric series? Agreed, that's a disguised geometric series. So if I stick a sigma in front of these two guys, what do you know about a geometric series whose R value is 1 over e? Converges or diverges? R value is 1 over e. Okay, is 1 over e less than 1?
Converges.
So that makes it converges. So you can then just say, by the comparison test, series converges. In a way, don't you have to know what the answer is so you can figure out what to do over here? You have to know it converges, or you have to kind of assume that you know it converges. Let's look at that guy. E to the 2 over n. Now it's not e to the 2n, that's a different story entirely. It's e to the 2 over n, right? So basically, as n gets bigger, doesn't e to the 2 over n get smaller and smaller and smaller, right? So that's important. Now, here's the problem that we're going to have to fix. I need to take this fella, right? And I know that this is going to diverge. Because isn't it a little bit bigger than 1 over n? And so I can write down that. And I know that's a p series and p equals 1 and that's less than or equal to 1. So I know it diverges. So by the comparison test, my series diverges. Now, every time I've done this comparison, it had to be true. I can't just, you know, like the one where I said 1 over n and then I paused for a minute and think, wait a minute, 1 over n might not always be true. Isn't there some values of n where this wouldn't work? So I had to say, okay, 2 over n, I think was the suggestion someone gave. I just went overboard and said 10 over n. But wouldn't 2 over n work equally fine? This one is so weird and so easy at the same time. Remember n factorial? Right. Is that thing going to converge or diverge? Just by looking at it, can you get a gut feeling, is that going to converge or diverge? 9 over n factorial.
I think it would converge.
Yeah, it converges very, very quickly, actually. Which means then that I have to prove that that's less than or equal to something else, I guess. Great. So who? Well, how about 9 over n squared? Well, why can I get away with that? Isn't that 1 times 2 times, but towards the end, isn't it an n minus 1 and an n? Would you agree that that's going to be massive and that's not quite as massive? All right. And so smaller numbers, bigger fraction, bigger numbers, smaller fraction. This is true. And we know this guy, he's a p series. The p value is 2, which is greater than 1, so it converges. And by the comparison testing, our series converges. You just have to prove to me, this is not the only correct answer. Couldn't have said it was less than or equal to 9 over n cubed. And that would have been equally correct. I couldn't have said 9 over n because I would only be proving that you're smaller. I mean, it's true that it's less than 9 over n, but wouldn't that just say I'm smaller than somebody that diverges? Now, the logic of that doesn't mean that you converge, right? Just because you're smaller than a zillion, right, doesn't not mean that you couldn't still be huge, right, and diverge, right? So don't get caught up in that little idiosyncrasy. 16. I'm putting this 4 in for a reason. I know this is a this is a comparison test. Would you agree? Because it's got some funny, I don't know how else to be explain this, but isn't that weird stuff, right? E to the 1 over n, sine squareds, n to the weird power, like 1, all basically weird stuff. Who is this guy going to be?
Greater than n to the 1. 1 over.
Oh, 1 over? Okay, you're going that way? So what does that make it? Bigger than a diverger? And if you're bigger than a diverger, what does that mean? You diverge. Sounds right, doesn't it? Fortunately, it's wrong. What I'm going to do is prove that it does diverge, right? But I'm going to do that as my comparison, which is the same. And I'm going to do a limit comparison test. And I wouldn't choose to normally do that, but there's always exception to every rule. So we have 2 over n to the 1 plus 1 over n divided by 1 over n. It's going to be the limit as n tends to infinity of this guy times that guy. I'll try to take this as slow as I possibly can. Okay, can anybody see a way of simplifying this weird fraction? Because it can be done.
Can I split that thing into n of power 1 time n to the 1 over n?
I like your thinking, and the answer is yes. And if you do that, don't you cancel? And now you are left with the limit as n tends to infinity of 2 over n to the 1 over n, right? And now I'm going to tell you a truism, which you are going to believe, because I'm telling you, and I'm a mathematician, that n to the power of 1 over n actually is equal to 1. Now, there are a couple of magic guys that we have met. Let me remind you of the other one. Can you remember I told you that? Oops, that's a B. Can you remember I told you that magic guy? 1 plus a over n to the power of b over n is e to the ab. Remember, just said it is, trust me. If I don't remember me telling you, I did. Right, here's the second and last magic one. Is equal to that. Okay, I'll prove it to you then. Don't need to know this, but for fun and giggles, let me prove that this answer is correct. Okay.
Just brute force it.
Unfortunately, infinity to the power of 0 has a problem. I know anything to a 0 is 1, but not infinity. It might not be 1. It happens to be 1, but it might not be. So I'm going to call this guy, I don't know, y. Okay. And now I'm going to find the limit as n tends to infinity of y. And it's going to be the limit as n tends to infinity, right? Of that guy, right? So far, so good. Now, I'm going to take the log of that guy. Okay. And I'll do the limit again, because I just realized that I needed this fella. That guy. You with me so far? Right. Now, don't worry about that. We'll sort him out later. Right. Let's do this guy. Couldn't you do L'Hopital on this? What would you get? You'd get the limit as n tends to infinity of 1 over n over 1, which is basically 1 over n, which is 1 over infinity, which is 0. So the natural log of y is 0. So that makes y e to the power of 0, which is 1. And isn't y that guy? Yeah. No more magic. Have I convinced you then the n to the power of 1 over n is 1? You know that's probably the only time you're going to get to use it, but at least you got to see it. Right. And that's that out the way. I think we are done for that section. So let's get a head start on the next one. Bear with me for a few moments. And our next section is 11.5. There's a lot of writing in this heading. Show you what it looks like if I haven't already got it set up. Oh, good, I did. Right, there it is. We are going to look at what are called alternative, let's get that word out, getting tired. Alternating series, right? And absolutely convergent series. So that's kind of what whatever's left of today is going to be about. So let's show you what an alternating series looks like. Alternating series look like this. They have a -1 to the n, a -1 to the n plus 1, or a -1 to the n minus 1. The reason they're called alternating series is that when you calculate them, you get, let's pick one with numbers in it so we can see it a little bit clearer. Let's suppose I do this one. If you plug in 1, you get a positive answer, and then you get a negative answer, and then you get a positive answer, and then you get a negative answer. Do you see how it goes plus, minus forever? Or it goes minus, plus forever. So the alternating that they're talking about is the alternating in the signs. These are called alternating series. This here is a generic version of it, right? That's pretty much all of them could be made to look like that, right? Now the alternating series test not surprisingly, is only used on alternating series, right? So don't use this on any other series except the ones that go plus minus, right? The ones that look like this. And the alternating series test says the following. If the individual terms, right, the little ENs, right, not the sum, not the -1, just the little ENs. So in this case, it would be that guy there. Is the little ENs positive and decreasing? If they are positive and decreasing, then the series, the alternating series, will converge. If the series is positive and increasing, so each term's getting bigger, right, bigger than the one that came before and increasing, then the series will diverge. Right? With one extra piece of information. The limit of all of the terms has to be 0. Well, let's take the one I just wrote down. I wonder if this alternating series converges on them. Well, the EN is 1 over n squared. Would you agree that the limit of EN, which is the limit as n tends to infinity of 1 over n squared, couldn't I just brute force that and say the answer is 0 with almost no working at all? Right, 1 over infinity squared is 0. Now, is it positive? Yes. Is it decreasing? Well, if I want to prove something's decreasing, I need to show that its derivative is negative. Didn't we do that in the integral test as well? So I'm rewriting it in this format so I can do multiply by the power, reduce it by 1, then make it look pretty. And then say -2 is a number that's always negative. N cubed is always positive, because remember, these questions always assume that n is 1 or more. A negative over positive is negative. That makes this function decreasing. Well, positive and decreasing, and its limit is 0. We are good to go. By the alternating series test, then, our series, this one, converges. Are we cool with that? Just, I mean, okay, it's a basic one, but that doesn't make it any less so. Let's try an ugly one. You take that one. Then we're going to focus on the behavior of this term here. Would you agree it's positive? What about the limit? Would you agree it's 0? Prove it to me. What method would you use? Because there's only one method I can think of that would be able to prove that that limit is 0, which is?
Relative rate of increase.
Okay, you've just proved to me wrong. There are 2 ways to prove that that is 0. I forgot all about relative rate. Which one was I thinking about? But relative rate is fine, so keep it. What was the other one?
Can I do L'Hopital?
I would do L'Hopital. Well, at least that's where my brain was. And brute force there. Agreed 0, but relative rate works totally fine. In fact, in a way, I should have probably picked that one. Isn't it easier? Quicker, right? So all we need to do now is prove that this thing is decreasing, and we're done. And if it is decreasing, then this fella, right, converges. Now, if I prove it's increasing, then isn't this guy divergent, right? You don't get so many divergent alternating series, but I guess they could have. So the limit is, what am I doing limit? So f of n is that guy. I'm going to rewrite it like that guy. I just think product rules are easier than quotient rules. That's the only reason. So its derivative is going to be f dashed g plus f of g dashed. I'm making that f, I'm calling that g. It's going to get me 1 times that guy plus that guy. And if you differentiate this fella, you get e to the negative n times the negative 1. If you pull out e to the negative n as a common factor, you get that. And if you want to make it look pretty, it looks like that. Are we comfortable about the derivative looks like that fraction? Okay, here goes proving it's negative. If n is 1 or more, would you agree e to the power of n is a positive number? As long as n is reasonably big, so I guess I'd have to start at 2, but would you agree 1 minus n is essentially negative for almost all its life? So that counts as negative. So you're allowed a little bit of wiggle room. Do you know how normally I say n is greater than or equal to 1? The wiggle room is you can say n is greater than or equal to any fixed value. Like if it takes to 100 before everybody's negative, that's still counted as okay. And the reason why that works is, can you add up the first 100 terms and then the rest converges? So it's still okay. Now this is negative, which we know means decreasing. Bingo. We are looking at, by the alternating series test, the series will converge. Okay, let's show you a diverging one, if I can. Yeah, can't think of a clever one, so I'll think of an easy one instead. Right. Now, the en term is n squared over n squared plus 1. So far, so good. You agree it's positive, so that bit's done. Watch what happens to the limit as n tends to infinity. Would you agree that I could get the answer 1? I don't need to find out if it's increasing or decreasing, because if it levels off at 1, aren't I going to be adding an infinite number of 1s, and wherefore it diverges? So by the alternating series test, the series diverges. So it never even got to the third hurdle. Didn't it fall on the second one? That the limit wasn't 0. If the limit of a individual terms is any number, 1, a half, a tenth, aren't you going to reach a point where all the numbers are basically the same number? Right? Which means you're going to have a whole load of stuff that adds up to 42. And then you're just going to add 1, take away 1, add 1, take away 1 for eternity. Do you see why that can't converge? Because won't you go 43, 42, 43, 42, 43, 42 forever, right? Isn't it going to bounce between two values? So it's going to diverge, not because the answer is infinitely big, but because the answer doesn't home in a unique value. So this one died on that stage, right? Does that make sense? And we have reached a nice conclusion point. So put your last name down for attendance. Just your last name, that's all. And I will see you on Thursday. And I'll hang about for any homework questions or whatever you might have at the end of class. So, yes.
Question, could you go back to the give me just a second. The rule of the comparison limit comparison test.
Oh, that's a fair bit back. Let me see if I've got it somewhere handy. Is it the comparison test or the limit comparison test?
The limit comparison test, like the rules of it.
Okay. I'll start here and kind of go there. Here we are. That page there.
Yes, I haven't actually caught on to it. Can I well, hold on. I think there's a better way.
Right, while you're thinking of what you're thinking, has anyone else got another question?
Yeah, I was wondering, you mentioned earlier, like, there is, I think, what is it? The limit comparison test or
Mhm.
something like that. You mentioned sometimes people try to use like only one of them and then they get like half the problems run on the
Yeah.
test. I didn't catch which one was that.
Oh,
You don't want
if
us
you
to use-
try and use the comparison test, right?
Okay.
You will, my experience is half the time you will pick a good comparison and you'll get the right answer. But half the time you pick a bad comparison and you get the wrong answer. And the reason for that is that you typically will be tempted to do it. You know that ugly one, n minus 1 times n squared plus 1 cubed over n squared plus 4, and all that carry on. See that ugly one? You're tempted in those situations to say, I think it behaves like 1 over n squared and that it's smaller than it. And it actually behaves like 1 over n squared and it's bigger than it. And it might be so big compared to it that it actually diverges. Because the logic, you got to be careful here. If I have a divergent series here, right? If my series is less than that, right? That does not mean that I converge. Can't you be less than a divergent series and still be infinitely big?
Yeah, you can be
You
one
see the logic of that. And if you do a comparison test and you go this way, right, you make it go that way, you may come to the conclusion, oh, it's less than this guy, so less than, it means it must be, if this is bigger, that means that's less. It must converge. And it's not. It actually could diverge, but it could also converge. And
yeah.
so if you want to make it
That
work,
makes sense.
you got to make it work. Your guy has to be bigger. Because if you're bigger than something that diverges, right, the logic is you must diverge, right? Because if that adds up to infinity and I'm bigger than you, I'm going to beat you, right? I'm going to be even bigger. And the other one says then, okay, if you're converging, right, my guy hasn't it to be smaller. Right? And I just wrote that wrong way down, didn't I? No. And the logic here is, well, if my numbers are smaller than you, and you converge, I will converge. Right? If my numbers are bigger than you and you diverge, then I will diverge. But the other two permutations are not true. You can be bigger than a converging series, right? So your guy is bigger than some series that converges, but couldn't you still converge? And couldn't you still diverge, right? You see, you don't really know.
It makes
And
sense.
if you,
Thank you.
if you're going to do the limit comparison test, you must pick somebody that's true, right? Something that logically is allowed to be done. And half the time we don't. Yeah, have you figured out what you wanted to ask me, Gat?
I just need that page to
Okay.
record down. I didn't catch it.
Okay, I can leave it that. You can just watch the video and put a pause page on it sometime if you want as well, and write it down that way. Right. Jarrett, you got any questions for me? No, you good? Jessica, you good? You got a question? You're good. Okay. Anybody got a question then before I close
Question.
off? Hmm?
Question is the comparison test. Is this still applying the which series conversion diverge, right?
Yes, you're still comparing it to somebody that you know converges or diverges.
See it
And
now.
you're still going to compare it to typically a P series or a geometric series, right?
Yes.
So that part is very similar to a limit comparison test, right? The guy you compare it to is very much the same kind of situation. It's how you compare them, how you put them together, the trick. That's where the issue lies.
I had a question.
That's all.
So with the limit comparison test, so if it equals a number, not zero,
It's
but
not zero. Yeah.
it converges.
It behaves the same as the comparison. So if the comparison converges, it converges. If the comparison thing, right, the BN diverges, it diverges. It behaves the same as it.
So like, for instance, you look at problem 8.
Okay. What was problem 8 look like?
So it was the limit, the sum. It was the sum of 5n over 4n minus 3.
Okay, now I'm looking at that guy and I can tell you right now, that guy's in trouble. That's going to diverge.
Yeah.
Here's my comparison.
Mm-hmm. So yeah, I was looking at the problem and
It behaves like the number 1.
yeah.
Well, wouldn't an infinite number of ones diverge?
Mm-hmm.
And if you use that as your BN, you would do that fella, which is AN, over 1, which basically just ends up being the same guy on the top, which becomes eventually 5/4. And according to the limit comparison test, if the limit is a number that's not 0, it behaves the same way this does. And how does a series that's made up of an infinite number of ones behave? They diverge.
So on the notes, I have it. So I have it here that the limit as n approaches infinity of 4n.
4n. Is there more to that?
I'm just looking at it now. Oh, so I have right here, it says the limit at 4n over 4n minus 3 equals 1.
Yeah.
This was later on when you were working through the problem.
Right. So in this case, it's essentially the same, isn't it?
So I was just wondering if the by the limit comparison test, if it equals 1, why does it diverge? Why am I getting different answers? If that makes sense.
Why if the comparison is 1?
Mm-hmm.
Right. Well, if the comparison is 1, you're saying that this thing behaves like an infinite number of ones.
Yeah.
Well, if you go 1 plus, to me that is like guaranteed divergence. Okay.
Mm-hmm.
So that's not what your problem is. So are you comfortable with this fraction behaves like 1?
Yeah.
Okay. So according to the limit comparison test, if you take the original and you divide it by the comparison, which in this case is 1, gets you that, which eventually gets you that. Now, according to the limit comparison test then, if the limit is a number that's not 0, won't my guy behave the same way that sigma 1 behaves? Right. The problem I think you're getting here is that this is 1. If I had said to you it behaves like 1 over n, would you have had a problem that it diverges?
No.
Isn't 1 even bigger than 1 over n?
Mhm.
Well, wouldn't that diverge then?
Yeah, it would, but so I'm looking at other problems though
Mhm.
that are similar, like for instance, number 9.
Okay. And what's 9 got in it?
So the sum of n plus 1 over n5 n to the 5th
Mhm.
plus n.
Okay, so that behaves essentially like a 1 over n to the 4th.
Mhm.
And we
Yeah.
know that converges, don't we?
Yeah.
And when you do the limit as n tends to infinity of en, which is this guy, divided by bn, which is this guy, the answer comes out as a number. And according to the limit comparison test then, if the limit of this is a number, then this guy behaves like that guy. So that means it converges.
So if the thing right here, just supposing it did, the limit of n as it approaches infinity, if it were to equal 0, would that mean
Then you have chosen a bad guy here, and you cannot do the limit comparison test.
and we
If
have to
the
redo it?
answer is infinite, you've chosen a bad guy and you can't compare the thing either. So you got to pick a good comparison guy that doesn't generate a limit of 0 or infinity.
Okay, so I think I'm now getting this. So
Right.
when we're doing the limit comparison test,
Mhm.
it's just verifying that we picked a valid comparison.
Yes.
Is that- Oh, so that makes much more sense now. Okay.
It's a check that you've done it, and it's also the proof that you've done it right as well, I guess. Check, proof, check. I guess you could interchange them. Right.
So that
Alright.
equals
And-
1,
yeah.
not 0. So that says it's n over bn is 1. So
Yes.
would that diverge because it's not 0?
No,
No. Well, don't get that idea in your head. Throw that idea right out of the head right now.
Okay.
If the limit between an over bn is a number, 1 is just a number, right? Could be 2, it could be 22, but it's 1. If it's a number, then this guy and this guy behave the same. And we know this converges, so that converges. So what Tom was saying is, what happens if I do and I get a limit of 0, or I do the limit and I get that, those two guys. What that has said to me is that I have chosen a bad comparison. The limit comparison test is no longer usable because I don't know whether this guy behaves like him or not. And the reason I don't know it is because the limit was 0 or the limit was infinite. As long as it's a number that's not 0, we know that this and this behave the same. Right? So that is fine. Now, there is ones floating around here, which is a totally different one. Isn't this a P series? P equals 1 diverges. Isn't this P equals 2 converges? You see there's a 1 and a 2 floating about here. And isn't there a half to the power of n and a 7/4 to the power of n? And isn't there a rule that says if r is less than 1, it converges, and if r is greater than 1, it diverges? Right. Do you see that there's a 1 floating around here? Have you noticed that the one's pointing in a different direction? Big P means converge. Big R means diverge. Small r means converge. Small p means diverge. You notice that they're actually kind of talking, I mean, these are truisms, right? But aren't they not going the same way? So you have to say, oh, it's a P series, this is what's true. It's a geometric series, this is what's true, right? And when you do or find this guy, right, he's going to fall into either a P series and you use this rule, or he's going to form, it's going to become a geometric series and you use this rule. But if this limit is not a number, right? If it's 0 or infinity, you've screwed up here. Now, I don't know how you screwed it up, but you know, maybe you dropped a power somewhere, right? You put 1 over n cubed when you should have put 1 over n squared, you know, something like that, right? But whatever it is, it's wrong, and you need to go and fix it because you haven't proved anything until you show that this ratio, the limit of this ratio, is a number. It just happens to be 1 as a common answer, but there's no reason for it to be 1. I mean, I could make a question and make the limit 2 and it would be fine. It'd still converge.
But generally, everything usually comes to 1.
Usually because of the way I do the simplification. Because some people say, well, imagine that was 2 and that was 3. Wouldn't I still call it that guy? Right?
Mm-hmm.
Now, if you did that one, you would find out that the limit was, I think, 2/5 or 2/3. It'd still be a number and it'd still converge. Right? So it's just the way I choose to do the surgery that tends to generate 1 a lot. That's just the way it is. It's not significant about the number 1. We just care that it's a number. That's not 0.
I think I had one more question.
What you got?
So it's from the homework from
Mhm.
11.3.
Is it a quick one you can read out to me, or shall I go looking for it?
I think I can read it out to you.
Right.
Let me quickly find it. It's the sum from n equals 3 to infinity of n to the negative 0.
No, I didn't catch that after the n equals 3 infinity.
Of n to the negative 0.999.
That guy, right?
One more 9, but
That guy.
yeah.
Well, here goes. If I rewrite this one so it looks like a P series, it will be that guy. Okay?
Mhm.
And it's a P series because it has 1 over n to the power. P series don't need whole numbers there, right? Can you have
Yeah.
n to the half and then to the point, lots of 9s? But the P value for this guy is 0.9999, which is less than or equal to 1, isn't it?
Mhm.
And what do you know about a P series if the P value is less than or equal to 1? We
It
know that it
diverges.
diverges. Now, are you meant to do that as an integral test, for instance?
Yes,
Right,
and I
so-
think I
right,
messed
so-
up on the integral.
Right, so if you're going to do that as an integral test, can we pretend that it's positive and decreasing? We've done all that stuff.
Yes.
And so all we're going to be looking at is the limit from 3 to infinity of 1 over x to the 0.9999 dx, right? Which is going to become the limit as t tends to infinity of the 3 to t, and I'm going to rewrite this guy as negative 0.9999 because that's going to be easier to integrate, right? Because I'm
Mhm.
going to use the power rule. So it's going to be the limit as t tends to infinity of add 1 to the power. You will get 0.0001. It'll be positive, right? Because you add 1 to that negative 0.999, you get that guy. And you'll divide by the new power, which is this guy here. And you're going to evaluate it at x equals 3 to x equals t. And so it's going to be the limit as t tends to infinity of, well, do you know that guy over that guy, I believe, is 10,000. Right?
Yeah.
Yes, I should check. Right, 10,000. I'm going to just leave that guy as a weird power because I can live with that. Take away 10,000 times 3 to the power of that guy. Right. Now I'm going to do brute force. It's 10,000 times infinity to the power of 0.0001. Take away that guy. That guy is just some weird number, right? It's just a number. I'm not too concerned about finding its value. Infinity to the power of any positive term, even if that positive power is a small number, is still going to be infinity. It might take a heck of a long time to get to be infinity, but it is. Right? Infinity to the power of half is just the square root of infinity, right? Infinity to the power of 0.1 is just the 10th root of infinity. But isn't the 10th root of infinity still infinity? So isn't that just an extreme version of that? Which means this thing is infinite. And if this thing is infinite, it diverges. Which we kind of knew because of the p-series, but now we've proved it.
So the second part of the limits is just proving it.
Well,
Is
this
that-
bit here,
Yeah. it's
this
proving
here,
it.
well, we kind of know the answer.
Yeah, we
Most
know
of
the answer,
time, you
but
know, we're actually proving it.
okay, that makes much more sense, I think.
So when you're looking at limit comparison test, we're basically proving it or checking it, if you prefer that term, that we've actually done everything the way it should be and everything, you know, lines up mathematically.
All right.
And so this here is that part. This also has the advantage of, couldn't I use this, an adaptation of this, of figuring out how many terms I would need to get, say, the sum corrected 2 decimal places? You remember that one where you would do n to, sorry, what would it be? Yeah, n to infinity, right? You'd find Rn.
Mhm.
I would think that question would be ridiculous. Do you know if you wanted something to 2 decimal places, you might have to add up something like 1,000,000 terms.
Yeah.
Yeah, I'm pretty sure if that's what it was. But since this thing diverges, you wouldn't even know it diverges, because even if you added up 1,000,000 terms, it probably wouldn't be, you know, it'd still be huge, but it, you know, it could be, well, it might not, it might.
Mhm.
Any other questions? Okay. See you on Thursday, everyone. Have a great, well,
Yeah, you
whatever's
too.
left of this evening.
Have a great evening.
Thanks for the extra time to answer questions.
It's okay. I will bill you later.
Yeah. Go get some dinner.
Yeah. Now, Jessica's, you didn't know this, but Jessica volunteered to pay for everyone.
Oh, thank you, Jessica. Very
Okay, bye-bye, guys.
Bye-bye.
Thank you.